So now we've seen how to set up the initial simplex tableau. We've seen how to read off the solution from the final simplex tableau. And now we just need all of the steps in between, which are the row operations. And here the row operations, or the procedure we're going to use for row operations, is called pivoting. I'll show you why it's called pivoting in a second. But this is the strategy that we're going to use for our row operations. So we're just going to go through these 5 steps over and over and over until we've made it so that there are no negative indicators remaining. And remember, once that bottom row has no negative indicators, then we want to read off the solution because it will be the optimal solution for the problem. Okay, so I would recommend just having this page in front of you, so maybe pull up the notes and have these instructions in front of you as we go through these problems. I'm going to quickly read over them now, but I think it might be useful to you to have these up on one page while you watch me do the problems on another page. Okay, so let's look at these steps. In step 1, it says you want to locate the most negative indicator, and that tells you which column you're going to be working with. So that will tell you the column that contains the pivot. So we start by attacking the most negative indicator, and then for each row in that column that has a positive value, we're going to calculate the constant on the far right side divided by that value in the pivot column. So I'll show you what that means in a second if that's a little too fast for you, but we're just going to compute a particular quotient. We'll take the far right number and divide by the number that lives in the column that we're looking at, and we'll compute all of those quotients for each entry that lives in the column that we're looking at. And the smallest non-negative quotient that we get will tell you which row we want to be working with. So that's step 1 and step 2. That identifies the pivot column and the pivot row. The pivot, or the pivot element, is going to be the element that lives in that column and that row. So these first 3 steps are just to locate the pivot. The goal then is to turn that pivot into a 1 and to zero out the rest of that column. So steps 4 and 5 are very similar to, well, I guess step 4 is very similar to what we would do in Gauss-Jordan elimination. We're going to use the division row operation to turn that pivot into a 1, and then we're going to use the other row operations to eliminate the rest of that column except for that pivot value. And by the way, in pivoting, we're never going to interchange 2 rows. So we're always going to be dividing in order to get a 1 where we want it, and then we'll be adding or subtracting the appropriate multiple of that pivot row to the other rows in order to eliminate the rest of the entries in that pivot column. And then we're just going to go through this procedure, repeat it over and over until you've reached the stage where there are no negative indicators. And down here, there's a nice little note that just says, if you're unable to pick a pivot column because all of the indicators are non-negative, then that means that you can just read off your optimal solution. So if there are no remaining negative indicators, then you're done. And if this procedure does not allow you to pick a pivot row, then that means that there is no optimal solution. So if you try this strategy and there's some problem with it, for example, there are no positive values in the pivot column or something like that, then what we would know is that there is no optimal solution to the original simplex problem. Okay, so remember, you can have this page in front of you. I'm going to refer to these steps as we go through them, but I'm not going to keep scrolling back up to see the instructions. So what we're going to do in this video is just work on problem 3 here. So in this one, we didn't have to translate the initial linear programming problem into a simplex tableau. Here we were just given the simplex tableau. It says use the simplex method to solve this problem. Okay, so I've already copied this initial simplex tableau onto the next page because I'm worried that we're just going to run out of space if I try anything here, and I can't conveniently scroll between 2 pages. So I'm just going to restart the problem here, but this is just the same matrix as on this previous page. I've copied it without the column headers. And by the way, this is typical. Normally, as we get comfortable with this procedure, we're not going to continue labeling each of the individual columns. So this is what you might see as a typical initial simplex tableau. So now let's talk through the pivoting procedure. So because there are negative indicators here, we know we shouldn't read off the solution right away. We want to get rid of those negative indicators. And to do that, we'll go through the pivoting process. First, we identify the pivot column. That's the one that has the most negative indicator. So negative 14 is the largest negative indicator, so this will be our pivot column. Now we need to decide the pivot row. And to decide the pivot row, we need to compute some quotients. So I like to compute these quotients off to the side. So I've written a Q up at the top there for quotients. And I'm going to compute these quotients. Remember, the quotient was the constant entry in that row divided by this entry in that row. So for each of these rows that have a positive value here, like this positive 2, positive 2, positive 4, positive 2, for any entry in the column that we're looking at that's positive, we would compute this quotient, and it's the quotient of the far right number divided by this number. So this would be a 40 divided by 2, which is 20. The next one would be a 60 divided by 4, which is 15. And then the next one would be a 24 divided by 2, which is 12. Okay, so here we choose the smallest value that we get. So the smallest quotient will tell you which row you want to work with. In this case, the smallest quotient is a 12, so we would be working with this row. And now we found the row and column for the pivot. That means that this is the pivot. So that 2 is the pivot. What that means is that we need to divide that row by 2 in order to turn that entry into a 1. And then we want to eliminate the rest of that column. So we can do this all at once if you'd like. I normally like to separate this into a couple of row operations. So I would maybe say that we're going to take row 3 and divide by 2 in order to turn the pivot into the appropriate value. So let me recopy the matrix real quick. So these top 2 rows are not going to change. But the third row, we're dividing by 2. So this would give us a 1, a negative 1, a 3, a 0, 0, a 1/2, a 0, and a 12. And then the objective row is also not changing. Now notice that here we did get fractions. So we have a fractional entry over here. In this procedure, that's just unavoidable. So we can't do any sort of clever trickery in order to avoid that fraction. Instead, here you just follow the procedure as it's written, and sometimes you'll get fractions. So for some operations, it might be handy to just have a calculator on hand. But now we've turned our pivot into a 1. The next thing that we need to do is eliminate all of the other non-zero entries in that column. So I would take row 1 and subtract twice the pivot row. And then I would take row 2 and subtract 4 times the pivot row. And I would take the last row and I would add 14 times the pivot row. So I'm going to do all of that in one step because these row operations don't interact with each other. So maybe I'll just to sort of anchor us somewhere, I'll recopy this third row. Because the third row is not changing. And now we'll compute these other rows. If I go a little too fast for you here, feel free to pause the video and work on some of this scratch work on your own. But for this top row, we're taking the top row and subtracting 2 times row 3. So this first entry would be a 0 by design. The next one would be a 2 plus a 2, which is a 4. The next one is an 8 minus 6, which is 2. And then we'll have a 1, and then we'll have a 0. And then this next entry is a little bit tricky. This would be a 0 minus a 1, so that would be a negative 1. And then we'll get a 0. And then a 40 minus a 24 would be a 16. So that's what we should get for the new top row. For the second row, we're taking the middle row and subtracting 4 times what's beneath it. So this would be a 0, a negative 5 plus 4, which is a negative 1, a 6 minus a 12, which would be a negative 6, a 0, a 1, a negative 2, a 0, And then this one would be a 60 minus a 48, which would be a 12. And if you'd like, if these are too fast for you, but you're comfortable with doing row operations, you can just sort of trust me on some of these values. But if you'd like, you can also just pause the video and double check me. So for this next one, we have row 4 plus 14, row 3. So we're adding 14 times what's above the bottom row. So this would be a 0. This would be a negative 10 plus a negative 14. So that's a negative 24. This one would be a negative 12 plus 14 times 3. That would be a 42. So negative 12 plus 42 is 30. And then this one would be a 0, a 7, a 1, and then a, what's 12 times 14? 144 plus 24. So I guess 168. Okay, so this is what we end up getting as our next simplex tableau. So we're not quite done here, because at this stage, we could read off the values of our variables, but we know that this would not represent the optimal solution because we still have a negative indicator. So we want to continue doing this procedure until we're done with these negative indicators. So our next line of attack is here. We have a negative 24 as our only remaining negative indicator. So that will be our pivot column. Now we need to decide the pivot row. Now the pivot has to be a positive number. So both of these negative ones are out. They cannot be the pivot. And you can scroll back up to the pivot rules if you want to check that. But neither of these negative 1 rows can be the pivot rows. So that means that this one must be the pivot. You could compute the quotient. That would be a 16 divided by 4. So the quotient here would be 4. But you don't really need to because that's the only possible pivot. So that will be our pivot. And that means that our first step is to turn that pivot into a 1. To do that, I'll take row 1 and divide by the pivot. So that'll be a row 1 over 4. That would give me a 0, a 1, a 1/2, 1/4, 0, negative 1/4, 0, 4. And then I didn't change any of the other rows yet. So the second row would still be this. And then that third row would still be this. And so on. Okay, so this is where we're at so far. And now we need to decide on the appropriate row operations. Remember that once you get a 1 where you want it, just like in Gauss-Jordan elimination, we're going to kill the rest of that column. So here what I need to do, oops, I copied this down wrong. So this 0 here, let me see if I can erase. I just copied the third row a little bit wrong. I should have a leading 1 here. Okay, so now we should be good. So now that we have a 1 where we want it, we're going to eliminate the rest of that pivot column. So for that, I would take row 2 and add the pivot column, sorry, the pivot row. I would take row 3 and add the pivot row. And I would take row 4 and add 24 times the pivot row. So this top row is not changing, so I'm just going to copy it down. For the second row, I'm adding what's above it. So this would be a 0, a negative 6 plus a 1/2 would be, I guess, a negative 11/2. This would be a 0 plus 1/4, so that would be 1/4. This is 1. Negative 2 minus a 1/4 would be negative 9/4. You can also do these with decimal entries if you'd prefer to do that. That's fine with me. So if you would rather do a negative 2 minus a 0.25 to get a negative 2.25. That's fine with me. And then this one would be a 12 plus 4, which is 16. And then for the third row, we're also adding the top row. So this would be a 0, a 3 plus 1/2, which would be a 7/2. This one is a 1/4 as well. This is a 0. This is a 1/2 minus 1/4, which would give you a 1/4. This is 0. And this is a 12 plus 4, which is again 16. So that's what we get for those top 3 rows. And then for this bottom row, we're adding 24 times the top row. So this would be a negative 24 plus a 24, which is 0. This would be a 30 plus 12, which is 42. This would be a 0 plus 6. This one would be 0. This one is a 7 minus a 6, which is 1. This one's a 1. And this one would be 168. Oh, no. This is 168 plus 4 times 24. So I'm actually going to bust out the calculator real quick. So we have 24 times 4 plus 168. That ends up being 264. All right. Now this actually is our final simplex tableau. That's because there are no remaining negative indicators. So we're done with our row operations. Now we just need to read off our final solution here. To do that, it might be good to relabel the columns. So remember, this was our x1, x2, x3, s1, s2, s3, z, and c columns. So now I'm going to read off the optimal solution here. Remember that in order to read off the optimal solution, maybe I'll change the colors here. In order to read off the optimal solution, we first eliminate any of the columns that have too many non-zero entries. So I would eliminate this column as being non-basic, this is non-basic, this is non-basic. You don't want to eliminate the constant column. So the constant column does not count as one of these variable columns that could be either basic or non-basic. So we do keep the C column at all times. But for any of these variable columns, if they have more than one non-zero entry, we kill that column. And now we can read off the solutions for these. Instead of reading off the equations row by row, I normally like to read them off in the standard order for our variables. So I would read off x1. To do that, I would be reading this row, and we get x1 is equal to 16. Just to make sure that you understand what's going on, I want you to maybe pause the video if you need to think about it, but what is x2 here? So I get an x2 value of 4. For this one, you might also need to scroll back up to the rules for reading off solutions here, but notice that the x3 column is scratched out. So what's the value of x3? So this one should be 0. And normally, unless we're asked about the slack variables, I don't write them down as part of the answer because, again, we sort of invented them. So x1 through x3, those are part of the original problem statement. The slack variables we invented so that we could use this procedure. But the last variable that I would report is the optimal value for z, and that would be 264. And maybe before I end this video, there are 2 comments that I want to make. One is that if you look at the value of x1, x2, and x3, and so on, then what would happen if you were to draw pictures for all of these? Now, this would be a 3-dimensional picture because you have 3 variables that are changing, x1, x2, and x3. But let's say that this was a 2-dimensional problem. If you were to read these off, then what's happening is you have that the initial simplex tableau will start you at 0, 0, and then every time that you pivot, you'll be going to a different corner point. So here we would land maybe at the corner point 16, 4, if we had x1 is 16 and x2 is equal to 4. And you can also read off from the tableau the corresponding value of z. So at this corner point, we would get a z value of 264. And this procedure, because there are no negative indicators remaining, this procedure guarantees that 264 is the optimal value for z, and it occurs at the corner that we just found. So this is equivalent in some sense to the graphical procedure that we talked about last week. We're still just searching for which corner is going to give us the best value for z, but this procedure is giving us a matricial way of searching through the corners to find the best corner, rather than having to graph everything and then plug in literally all of the corners. And notice that in some cases, like in this problem, we would be unable to graph because this would be a three-dimensional graph. We have three free variables, x1, x2, and x3. So this would be a 3D graph rather than a two-dimensional graph in terms of x1 and x2. So, but just so that you have some handle on what this procedure is actually doing, this is just a way of searching through the simplex, going corner by corner until we find the best corner here. The second comment that I want to make is that notice that throughout this entire problem, let's look at the z column over here. So this was the z column. The z column was 0, 0, 0, 1, and then 0, 0, 0, 1, and so on. And then at the very end of the problem, it was still 0, 0, 0, 1, and the corresponding equation told us that z was equal to 264. So this is actually going to be true in all simplex method problems. You will always have a z column that looks like 0, 0, 0, 1, or some number of zeros and then a 1. And your final equation will always tell you that the value of z is equal to this value that lives over, The final equation will always tell you that z is equal to this bottom right value. So some people like to, instead of drawing this z column over and over, some people like to just omit this column altogether because it's always going to stay the same, and instead they would identify z with this bottom right entry. And that's fine with me. So if you want to stop writing the z column, then you can just remember that z will be this bottom right entry at the very end of the process. But it is still important that whenever you set up the problem, the values that you get, so I'm actually going to delete those just so that it's a little more legible, but it is still important, even if you do decide to omit the z column, that these indicators, the -14, -10, and -12 up here at the beginning of the problem, those do need to come from rearranging the initial equation. So if you started with something like z is equal to 14x1 plus 10x2 plus 12x3, even if you do intend to omit the z column, we would still rearrange this so that it looks like -14x1, minus 10x2 minus 12x3 plus z equals 0. And then this would translate into this bottom row that we have over here, but we would be omitting the z coefficient. And then we would just remember at the end of the day that this bottom right entry is what represents z. So it would be okay to omit the z column at all times if you'd like, but you will still have these negative coefficients because we do still in principle need to be rearranging the initial equation in order to write these coefficients for x1, x2, and x3, and so on. So that gives you some option for not having to write as much. You can just delete all of the z columns. We'll start doing that next week, but for today I'll continue writing the z columns. So we have one more example problem. We've now seen the full procedure, so we now know how to do everything here. And in this last problem, we're going to put it all together.